is the distributivity property true for the intersection with the union? So this is similar to really asking is something like x times y plus, I'll call that z, the same as saying x times y plus x times z, right? This is our x, that's our y, that's our z. It's not the same, but it's akin to this sort of proof is what we're trying to show here with the brackets. So how do we know if this is true or not? Well, we should draw some diagrams or examples to see whether or not the left-hand side is going to be the same as the right-hand side. So let's go ahead and do that. So looking at our first case where all the sets are going to share something in common with each other, we're going to want to draw the left-hand side first. So B union C is going to be everything in B and everything in C. So let's go ahead and highlight that. Everything in B and everything in C. And then we're going to want to see what parts of everything in B and C intersect with A. So what parts of this shaded area intersect with our set A? Well, it's going to be just this part here. So we're going to want to erase the parts that don't. So there we go. We're interested in this sort of intersection. Are we going to find the same shaded area on the right-hand side? Well, let's have a look. We want to look at first A intersect with B. So what part intersects between the sets A and B? Well, it's going to be this shaded in area over here. Fantastic. And then we're going to separately want to look at A intersect with C. So what parts of this have A and C intersect? Well, it's going to be this part here. And then we're going to look at the union of the two. So we're going to want to have both of those shaded in. And that's true. That looks exactly like the left-hand side. So let's go ahead and have a look at the second example where maybe only A and B share some elements, but C doesn't share any elements with either of the other two sets. So what does B union C mean? Well, B union C means we're interested in everything in B and everything in C. Fantastic. And then we're going to want to see what part of this intersects with A. And the only parts of this that intersect with A is going to be this part here, right? So we're only going to want to be interested in that part there. So we're going to want to erase the rest of these. I think that should be correct because everything in B and C, whichever part of that shaded area shares something with A. Yeah, okay, I think that's right. Let's have a look at the right-hand side. So A intersect with B would mean we're interested in this part. A intersect with B. And then separately, A intersect with C is where there's nothing for us to shade in because A and C don't share any elements together. So you want everything here and everything here. So everything in this plus nothing. So that's just going to leave us with this. And yes, the images on the left and the right do look the same. So that's probably true for these examples. But let's just be a little thorough and check it for two more. Okay, so let's have a look at what if the A doesn't share anything with the other two sets, but the other two sets do share something in common. So let's have a look. We want everything in B and C, so that's going to be everything in B shaded with everything in C shaded, so it's this big area. And we want whatever this part shares with A, and obviously none of this shares anything with A because they don't intersect, so we just erase all of our blue here. So on the right-hand side, we're going to look for basically nothing to be shaded in as well. Is that going to be true? Well, let's have a look. A intersect with B, well, there's nothing for us to shade in since A and B don't share anything, and similarly, A intersect with C, A and C don't share anything, so there's nothing for us to shade in. So it's the union of basically nothing, and that's going to leave us with nothing. So this is in fact true for this case. And let's look at the last case here where none of the sets share anything in common. They have no intersections. Is this going to hold? Well, let's have a look. B union C is going to be everything in B, shaded with everything in C. And then we're going to see what part of this intersects with A, and the answer is nothing. None of these shaded areas intersect with A. So we just erase all the blue parts that don't intersect with A, and we'll be left with exactly the image we want to find on the right-hand side. So we want to find an image on the right-hand side where nothing is shaded in. So we're going to find that. Well, A intersect with B is going to be nothing for us to shade in, and A intersect with C is also going to be nothing for us to shade in, and the union of two nothings is still nothing. So the image is going to be the same on the right-hand side. Okay, I just want to make a quick note about an example that I don't do too often. It's because it's not really too important. These are a little more important to think about. And that's going to be the example where you have a set within a set, maybe within a set, right? Like these kind of examples where you have A, B, and C, right? So B union C is going to be basically the whole thing shaded in. And then if you had to look at this right-hand side, it'd be B intersect with C, B intersect with A, so everything in A, and then A intersect with C, so everything A and C share. So it's just going to be the same little part shaded in there. So we're going to find, oh, hang on. Is that going to be true? Let me actually do this one real quick. If we have something like this, let's shade this in first. So B union C, everything in B and everything in C is going to be the whole thing or I have my blue marker here, it's going to be the whole thing shaded in, right? Because we want everything in C, which just includes B and A. Fantastic. Is that going to be the same on the right-hand side? Well, B intersect with A is going to be A. Fantastic. Right? So it looks like... Oh, I didn't draw the left-hand side correctly. I am making a big fool of myself. So we want everything in blue intersecting with A. So what part of this blue part on the left-hand side shares something with A? Well, it's going to be just the pink part. Does the pink part equal the blue part on the right-hand side? And the answer is yes. So this case is also going to be true. All right, so to start writing the proof, we have to recognize this is an equivalence proof, which means we need to show everything on the left-hand side is going to be on the right-hand side, and vice versa. Everything on the right-hand side must also be on the left-hand side, which means they are subsets of each other, or mathematically, the following two cases must be true. So it's going to be these two cases that we have to show are true in order to prove our statement is true. So we're going to be checking to prove that both of these are going to be true. To start the proof, we have to recognize this is a for-all proof. Why is it a for-all proof? Well, we don't have any restrictions on any of our sets A, B, and C. We're not saying if they have to all share something, if they have to exclusively not share something. That's why I did so many examples to make sure this is going to be true, which means that they can be any set A, B, and C. And for any, that's a for-all proof, which means we have to start with a let. What do we let? Well, we're going to let A, B, and C be sets. Fantastic. Okay, now we can get into proving our first case. Okay, so for our first case, we're going to need to show the left-hand side is not equal to. It is going to be a subset of the right-hand side. So what are we going to do? Well, we're going to show that if we have any element in the set on the left-hand side, so we're going to create any element like x, if any element here can also be an element in this set here, then that means every element here is going to be in this set here, which makes this set a subset of that set. So how are we going to do that? Well, first let's break apart what it means for x to be an element of this set here. Well, it means that x must be an element of, maybe let's get a better marker. It means that x must be an element of B and x must be an element of C, or this is an or statement because it's a union. And on top of these two, x must be an element of A. There's no question about x needing to be an element of A. Okay, fantastic. So what can we get from here to here? Let's think. So we're looking to get these two sections, and then we can say, well, if it's in this, it's definitely in this. If it's in this, it's definitely in the whole thing as well. So how are we going to get A intersect with C? Well, we can take the two cases here. If it's an or, we'll say, well, if x is in B and x is in A, right? Because x is always going to be in A, so this just carries over here. What we're going to say, let's take x is in B, right? And that means x is going to be in here, in A intersect with B, which means it's going to be also in A intersect with B unioned with anything. Okay, fantastic. The second case is going to be if x is in C and x is in A, because x is still going to always be in A, then we can say that it's going to be, of course, an element of A intersect with C then. And if it's an element of A intersect with C, then it'll be an element of A intersect with C unioned with anything, right? So, okay, this is the sketch of our proof. Let's go ahead and put this into words. We're going to start by supposing the element we created here. We're going to say, suppose x is an element of A intersect with B union C. Fantastic. Then we're going to want to do what we did here, which is break apart what it means for x to be an element of that set. So we're going to say then x is an element of A and x is an element of B, or x is an element of C. I'll put a bracket there, or sorry, comma. Okay, and now let's break it up into our two cases. So we'll start with saying if x is in B, then x is an element of B and x is an element of A. So x is an element of A intersect with B. Okay, fantastic. Yeah, okay. Might be a better way of phrasing this, but I think this gets the point across and you should get full marks for this. Let's do the second case. If instead of it being in B, X is actually in C, then X is in C and X is in A. So X is an element of, or actually we didn't finish the first case, did we? So we could say, so then if X is an element of A intersect B, then X is going to be an element of this right-hand side here, where it's going to be an element of A intersect B union with A intersect C. Fantastic. Okay, now we can get into our second case. So we say, if X is an element of C, then X is going to be in C and X is going to be in A. So X is going to be in A intersect with C. So then if X is an element of A intersect with C, then X is going to be an element of A intersect with B unioned with A intersect with C. Fantastic. So in both cases, it's going to be an element of the right-hand side. And now we can conclude that, therefore, since any element on the left-hand side is going to be an element of the right-hand side, we can conclude the left-hand side is a subset of the right-hand side. We can say A intersect with B union C is a subset of A intersect with B union with A intersect with C. Fantastic. Now let's do our second case. Okay, so for our second case, we just have to show the right-hand side is a subset of the left-hand side. We're going to apply the same strategy we did in our first case. But this time we're starting on the other end and we want to get back to our other side. So what are we going to do? We're going to still create a representative element. I'm going to call it Y in this case. So Y represents any element in this set. And if we can show that any element Y in this set can also be an element of this set, then since any element in this set can be here, then this makes this a subset of that, right? So let's go ahead and do that. So first thing we should do is break apart what it means for any element to be in this set. So it means that, yes, it means that Y is an element of A and Y is an element of B, or it means that Y is an element of A and Y is an element of C. Fantastic. Okay, so now we have to figure out how to get from here to here. How can we show that if Y is going to be in all these sets in this way, that it will also be in this set? Well, we already have that Y is definitely going to be in A, because in both cases, since we have an OR, we have two cases we should be considering. And in both cases, Y is going to be in A. So this part is covered. Now we just have to figure out how to get B unioned with C. Okay, well, we can say if Y is in B, that means Y is for sure going to be in B union C. And similarly here, if Y is in C, Y is for sure going to be in B union C. So since we have that Y is definitely going to be in A, and Y is definitely going to be in B union C, then we can say Y is in both A and B union C, which leads us to our conclusion down here. Okay, fantastic. Now let's put this sketch of our proof into actual proof words. Okay, so we're going to want to start by supposing the representative element we've created. So we're going to say, suppose some element, you can name it whatever you want, I'll name it Y, is going to be in A intersect with B union with A intersect with C. Fantastic. Then we want to break apart or explain further what it means for it to be a set of this, or an element of this set. We say then Y is an element of A and Y is an element of B, or Y is an element of A and Y is an element of C. Fantastic. Now we want to do both of our cases here. So let's start with the left case. We'll say that if Y is an element of A and Y is an element of B, then Y is an element of B union C given Y is an element of B. So Y is going to be an element of A intersect. Actually, maybe there's a better way of saying this. I'll say, if that's true, then taking y is an element of B, we can say y is an element of B union C, and thus, since y is an element of A and y is an element of B union C, then y is going to be an element of A intersect with B union C. Fantastic. Okay. Bit lengthy. I think that's nice and explicit. Let's now do the second case. So we say if y is going to be an element of A and y is going to be an element of C, then y is going to be an element of, I'll write it a little differently, element of B union C from y being an element of C. And so y is an element of A and y is an element of B union C makes y an element of A intersect with open bracket B union C close bracket. Okay, and now we just want to conclude that since in both cases our arbitrary element is going to be an element of the second set, that means the first set is going to be a subset of the second set. So we can say therefore, my markers are dying is what we need to say. Therefore, open bracket A intersect with B close bracket union with A intersect with C close bracket is a subset of A intersect with open bracket B union C close bracket. Fantastic. So we've proven both of our cases to be true. Now we just need to write our brief conclusion saying that since this is true and that is true, that means this is true. So let me go ahead and make some space to do that. Actually, no, I'll just write that over here. Maybe I'll use this marker instead. Hopefully it'll be nicer. So we can say, in conclusion, since A intersect with B union C is a subset of A union B, is it union? No, it's intersect. Union A intersect with C, and A intersect with B union A intersect with C is a subset of A intersect with B union C. I didn't really write this one very well. There we go. Then we can say A intersect with open bracket B union C is equal to A intersect with B close bracket union open bracket A intersect with C close bracket. So there we go. We have shown that this statement is in fact going to be true.